last time, we proved, I mean, we are interested in studying the function bracket n from E to E that sends a point P to n times P. And we simply denote NP. It has two coordinates, right? So this is two functions, two rational functions, GNP and HNP. So GN and HN belong to the field of rational functions. And we defined, of course, En to be all the points in E over K bar, such that NP is zero, the zero element. And we would like to study Gn and Hn in order to understand the group of n torsion points. And what we showed, we had a theorem for algebraically closed field. Gn and Hn are irrational functions. And their poles, of course, precisely at En. And moreover, En is finite for every n. And what I want to do now is start doing the formulas for G2 and H2. Let's write G2 and H2. So I remind you, we had the general formulas for how to add 2 points. Should I? Okay, so let me just write the formulas. This is I mean, you can extract, I mean, you can get these formulas by the general formulas of doubling of a point. G2 of a point P, for P is some x comma y on E. if you do G2 of P, you get the following expression. This is x to the 4 minus 2a x cube minus 8bx plus a square divided by 4sx, where sx is, as usual, is this x cube plus ax plus b. And the formula for H2 is y times x to the 6 minus 5a x to the 4 plus 20b, or I need more space. H2 of P is y times x to the 6 minus 5 a x to the 4 plus 20 b x cube minus 5 a square x square minus 4ab x minus 8b square minus a cube divided by 8sx square. So you will see soon that the details of the formulas don't matter that much, but I would want to consider the leading terms most of the time. And to study, well, we want information on GNP, HNP for some P. You know, we need some kind of anchor. And P, the only point in which we can hope to get information is the point at infinity, because the rest we have very little access to. So this is the next proposition. If n is a prime to a P, where P is the characteristic of the field, then if I take Gn is a function of x and y, right? And I divide it by x and evaluated at O, I get 1 over n squared. And if I do the same for Hn, but now divided by y and evaluated at O, then I get 1 over n cubed. Okay, so and this kind of give you a hint of what we're going to use it for, because this n square is essentially what we want. Um, we want to prove that En is isomorphic to Zn times Zn, and it would follow very easily from the classification of finite abelian groups if we know that En has order n square. Okay, so this general goal. And okay, so how do we of course the difficulty is that the formulas, the explicit formulas for Gn and Hn are not accessible. I mean, they explode very quickly. This is, if you want, it's one of the reasons that elliptic curves are used in cryptography. I mean, if you really want, I give you like a generic point xy, and you want to calculate. I mean, to calculate n times x comma y, the formulas become quite involved. So if you try to do brute force procedures, it becomes very expensive, and that's one of the reasons elliptic curves are useful in cryptography. So we don't have a closed formula. I mean, okay, I guess maybe at least for us at this point, we don't have a good closed formula for Gn and Hn. It's not accessible. It's very complicated, but we can hope that evaluating some expression from Gn at the point at infinity is kind of accessible. So the proof is by induction on n. And sorry, before I proceed with the proof, note this condition. So we really need that n is not divisible by p, because otherwise these functions behave very differently. And we will see also this this isomorphism is only true for n that is prime to p. Otherwise, it's not true, and the torsion points behave badly. So this is kind of the usual phenomena that when you take something in the characteristic of the field for which the elliptic curve is defined over, you get unusual behavior. But for integers that are prime to the characteristic, you get the typical behavior. This is how usually people see it. Okay, so by induction on n, first assume that n is smaller than p. And we need a base for the induction. So for n equals 2, I take the formulas and I divide, let's say I do gn divided by x and then evaluated at O. So what do I get? Sx is of degree 3, right? And if I divide by x, I mean the leading monomial here becomes x cubed. So evaluated at O, I have like a quotient of two polynomials of the same degree. And evaluation at O simply means you take the leading coefficient, I mean the coefficient of the leading monomial divided by the coefficient of the leading monomial in the denominator. And in this case, it's like it's 1 over 4, right? So I get for n equals 2, g2 at g2 over x at O is a 1 over 4, which is indeed a 1 over n squared. And now I do h2 divided by y, evaluated at O. Here, what will happen is that y will drop out, and sx square is, I mean, the leading monomial is x to the 6. So again, evaluated at O, I simply take the coefficient of the leading monomials and divide it by each other. It's 1 over 8. Now, I can write NP as n minus 1p plus p. And so if I do gn over x, I can write it as minus gn minus 1 over x and minus 1 plus 1 over x hn minus 1 minus y divided by gn minus 1 minus x squared. What I did here is, I mean, everything needs to be divided by x, right? I mean, I do gn divided by x, so this is divided by x. I have here I got 1 because I had I also had an x. This hn minus 1 minus y. Okay, so let me just remind you, we had it when we studied rational maps as points of an elliptic curve. I mean, just recall, if f is r comma s and g is what was it, t comma v, then f plus g, which is let's say k, and k is z comma w, then you get the formulas z, or rather, this is w comma z, sorry. And the formulas for w is minus t plus r plus lambda square, and the formula for z is minus v minus lambda w minus t. And this is assuming that, I mean, lambda could be either s minus v divided by r minus t, if r is different than t, and otherwise it is 3r squared plus a divided by 2s. Okay, these are the formulas for adding two points. And what I did here is I took these formulas and I divided everything by x. So let me just write it slightly better. So I have now n minus 1 p plus p. And what it is, so I need to take minus, this is this part. This part is minus t plus r, and of course divided by x. So what is minus t plus r? T is the guy in the first coordinate of the second point. I mean, so t is x here, and r is the first coordinate of the other thing. So this is so r is minus, sorry, is gn minus 1. Okay, so I did minus t plus r divided by x. Is this okay? This is it clear? Okay, and then in the second term, I took this lambda. This needs to be lambda square, right? But what is lambda square? Lambda square is, I mean, lambda is s minus v divided by r minus t. So, and s here is, of course, age n minus 1. And v is simply y. Okay, so this is, and I divided everything by x. Okay, so this is a formula for gn over x. And now I develop it a bit. I can write it as minus gn minus 1 divided by x minus 1 plus y squared divided by x cubed. And here I have h n minus 1 divided by y minus 1. And this is divided by gn minus 1 divided by x minus 1. This all is square. So what I did here, I just, in the second term, I mean, in this blue part, I multiplied by y squared from outside and divided by y squared from the inside. But dividing by y squared from the inside, I mean, I need to divide by y because I have this square here. So, and of course I did it because I want to use the inductive step. And in the inductive step tells me things about hn minus 1 divided by y and gn minus 1 divided by x. Okay, so now I evaluated O. Now I do gn divided by x, evaluated at O. This is just evaluating this expression, this orange expression, in each term. I mean, if I can evaluate in each term and it gives me a finite thing, then it means I can evaluate each term separately. So now by induction, gn minus 1 divided by x evaluated at O is 1 over n minus 1 squared. So I get the first term is minus n minus 1 to the minus 2. The second term remains 1. I evaluated O, I get 1, minus 1. And then y squared divided by x cubed evaluated at O is what? You remember? I have what is y squared divided by x cubed evaluated at O. Yeah, Lisa, go ahead.
Yeah, but my question is earlier.
Yeah. Okay, so go ahead.
I didn't understand this formula that you wrote for gn over x.
This one, the first one or the second one?
Yes, the first one. I don't understand what, like, I understand that I don't understand what stands for T and what stands for R.
Okay, let me try to explain. So I have np is equal to n minus 1 p plus p. This means that I can say that gn hn is equal to gn minus 1 hn minus 1 plus xy, right?
That's right.
I mean, I didn't write the variables of gn and hn and so on, okay? But so, but this is a addition of a rational maps, right? So take this one to be f, this one to be g, okay?
Mm-hmm.
And now we have a formula for how to add two rational maps. I mean, it's basically the formulas of addition of points on an elliptic curve, right?
Yes.
So the formulas are written here in orange. So I take R to be Gn minus 1, right? And S to be Hn minus 1. And then T and V are xy, respectively. And I have a formula for what is the result is like WZ. WZ is this Gn agent, right?
Mm-hmm.
And
Ah, I understand. Okay.
okay, and then I need to divide by x because I have division by x here.
Uh, okay. Okay. I understand.
Okay, so that's what
Thank
you
you.
get. Now, there is a subtle point, actually. How do I know that the lambda is S minus V divided by R minus T and not the other thing? The reason is that we had a proposition last time that Gn minus x is not identically 0. So Gn, which is R, is different as a rational function than T.
Mm-hmm.
Now, the reason Gn minus x is not identically 0, this we proved, but I can repeat quickly the proof. It's like if it was identically 0, then it would mean that P plus minus, or sorry, N plus minus 1P plus minus 1 P is equal to 0 for all P. And this would mean that either En minus 1 or En plus 1 is the whole E. And this is not possible because we proved that En minus 1 and En in general, Ek is finite. Okay, so this kind of this is the small pieces of the puzzle.
Yeah. Yeah. It's okay. Thank you.
All right. So we did this manipulation, and now we substitute. We substitute O in every point, and I need to see what is y squared over x cubed evaluated at O. Do you have an idea? Anyone? Yeah,
I'm
Elisa,
sorry.
you
Then,
yeah.
what do you mean by substituting 0 to every point?
I have a sum of rational functions here, right? In the
Yes.
and I need to evaluate this sum. I need to evaluate it at O. So
Yes.
if everything is, we had like a proposition that if everything is finite, you can evaluate each of the terms separately. Each of the summand, you can evaluate it O separately. It's not true. It's not always true. I mean, if one of the terms becomes infinity, then you need to be more careful. But if all of them are finite, then you can evaluate each of the summands separately and then sum it up. And
You
also,
mean that?
yes,
You
sorry.
mean that we evaluate just every term at 0, not at different points?
Yes, exactly.
I see.
And
I messed up something. Sorry.
yeah, no, it's like the terminology is not, we haven't fixed it well, maybe. But also here in the blue part, I have a product of two rational functions, and I need to evaluate this product at O. If one of the functions evaluated at O is not finite, then I need to be careful. But if both of them evaluated at O are finite, then what I can do, this we had like a proposition. I can evaluate each of the factors of the product evaluated at O separately, and then I multiply it. And so, I mean, I'm implicitly claiming that y squared over x cubed evaluated at O is finite. But what is it? How do we evaluate a rational function at O? You remember?
Like the exponents of the numerator and the denominator.
No, what it's about. So you have basically two. O, you can think of O as this heuristically. It's very useful to think of it as infinity comma infinity.
Yes.
Okay, so it means in the x coordinate I substitute infinity, and in the y coordinate I also substitute infinity. But remember that the degree of x is not the same as the degree of y. So I need to know, I mean, if I do, I need to know what is the degree of the numerator and what is the degree of the denominator. If the degree of the numerator is bigger than the degree of the denominator, then evaluated at O, I get infinity. Okay? If if the degree of the top is bigger than the degree of the bottom, then I plug infinity everywhere, then I get infinity. It's like if you evaluate x squared divided by I don't know, x squared plus 1 divided by x, you plug infinity everywhere, you get infinity, right? This just heuristically, you don't need to, I mean, there's no you follow me now?
Yes. Thanks.
So, but on the other hand, if I want to evaluate x divided by x squared plus 1, evaluated at infinity, this I get 0, right? Because this x squared is tending to infinity faster than x. Are you with me, Lisa, now, Nicolas?
Yeah.
Yeah. Okay. So what I need to do is to examine the degree of the numerator and the degree of the denominator. Now, if the last case is if their degrees is equal. If you have like x squared plus 1 and you have 2x squared plus 3x plus 2. And now you evaluate at infinity. What do you get if you evaluate this expression at infinity? Let me write it somewhere else. If I do x squared plus 1 divided by 2x squared plus 3x plus 2, evaluated at infinity, what do I get? remember you do this. Yeah, Nicholas.
1/2.
1/2 exactly. I simply take the leading coefficients. I mean, the leading the coefficients of the leading monomials, and I divide it by each other, because you can do a L'Hopital, and then you have like a 1 plus, you divide everything by x squared. You have 1 plus a 1 over x squared, and then in the bottom you have a 2 plus 3 over x plus 2 over x squared. And all these guys, they become 0 when x is infinity, right? So you are left with just the coefficients of the leading monomial. So this is in one variable, but in fact, in two variables, you do something very similar. But we have a convention that the degree of y is 3, and the degree of x is 2. So in fact, y squared over x cubed is a quotient of two polynomials of the same degree, right? Because the top has degree 6 and the bottom has degree 6 as well. So to evaluate it all, I simply take the coefficients of the leading monomials and divide it by each other. This is 1. Okay, so now I evaluate a gn over x at O. I need to evaluate the last expression, but the last expression I can write as the first factor, namely y squared over x cubed evaluated at O. This is 1. And then the second thing evaluated at O, but this I know by the inductive assumption. So I get a 1 over n minus 1, or let me write it as just n minus 1 to the minus 3 minus 1 divided by n minus 2 to the minus 2 minus 1. And this all is squared. Okay, and now I got some expression. You do the algebra, and you get that this is n squared. Sorry, 1 over n squared. Okay, I guess, yeah. It's I think from here it's really just like a simple manipulation. I hope you can believe me. I mean, I believe the book I took it from. And similarly, we can calculate hn divided by y at O to be 1 over n cubed. So this, if you want, you can take it as an exercise. Okay, we are not done yet, but maybe it's good to take a break here and come back to the rest of the proof. Do you have any questions so far?
I think I have one more question. Maybe it's simple, but I don't understand. How do you know that by induction Gn minus 1 is n minus 1 to the power of minus 2?
Well, this is like induction. You assume that the claim is true. The claim is that that Gn divided by x evaluated at O is 1 over n squared.
Ah,
So
okay.
right? So I assume by induction, I need to have a base case. This we had like the base case was n equals 2.
Ah,
Okay.
okay. Yes.
And then I of course deliberately I wrote Gn over x is stuff that are Gn minus 1 over x and Hn minus 1 over y, because then I can use the inductive assumption.
But how did we come up with the proposition? Like this assumption, where did we take it from? That Gn over x is 1 over n squared.
I want to prove it, so I want to prove it for all n. So I'm
Okay.
saying, for all n bigger than 1, okay?
So we just want to prove it, and we took n equals 2 as a base case. We showed that it is correct for n equals 2, and then we assume that it's just correct.
Then we assume it's correct for n minus 1,
Yes.
okay?
Yes, and that's what we did
prove
now.
it for n.
But we didn't do it for n yet.
No, look, we did a calculation. Gn over
Alright.
x. Gn over x, I first wrote the general expression, and then I evaluated it at O
Right.
using the inductive assumption. The inductive assumption is that when you evaluate a Gn minus 1 over x at O, you get a 1 over, 1 over n minus 1 square, right?
We used this assumption to calculate Gn minus 1, and we got the result for Gn that is exactly what we assumed.
How does induction work? You want to prove a claim for any n. Then you first check the base case, that the claim is true for n equals 1 or n equals 2, it's some finite n. And then the inductive process is you assume that the claim is true for n minus 1,
Right.
and then you prove the claim for n, right? You know this.
Yes.
So I assumed, my inductive assumption is that Gn minus 1 over x evaluated at O is 1 over n minus 1 square.
Yes, I understood. Okay, thank you.
Okay, and now I want to prove. I want to prove by induction. Using this assumption that Gn over x at O is 1 over n squared. So I write. Okay, you follow now?
Yes, I understood. Thank you.
Okay.
All
right, let's take a break and return to the proof. You can think in the break, what is missing, because let's say apart from the exercise, this Hn over y is it's a similar manipulation, but let's say we proved that Gn over x at O is 1 over n squared. So what else do we have to prove? This I leave you to wonder in the break. Okay. So what do you think? What is missing? I mean, look at the statement of the theorem. It has that n is prime to p. I mean, it's not the proposition is not supposed to be true if n is not prime to p. And we said in the beginning that we first assume that n is smaller than p. And we proved by induction, I mean, that for all n smaller than p, the claim is true. I mean, we had like a base, n equals 2. And then we proved that if it's true for n minus 1, then it's true for n. But we get stuck, we apparently get stuck when n is equal to p, because when n is equal to p, the claim is not supposed to be true. So how can we proceed with the induction? You see the point? This is a gap to fill, but that's not a big problem. So it appears we get stuck when n is equal to p, but we can circumvent it as follows. Instead of writing np equals to n minus 1 plus p, I can write np equals n minus 2 p plus 2p. So then I need to assume then I can kind of skip p, or skip n equals p, because I do the same thing that I did here. I mean, I open up, I have this these formulas here. Instead of x comma y, it's going to be whatever the formulas for doubling the point x y. And then, since I know by induction the claim is true for p minus 1, then I would I would take we take n equals I want now to prove the claim for n equals p plus 1. So for n equals p plus 1, I know the claim for I mean n minus 2 is going to be p minus 1, in which case the claim is true. You see? And then I would I would get the claim for n by the same procedure. Is this clear? Lisa, what do you think?
I'm sorry, I don't understand today things from first for this. I
No,
understand the first row that when you rewrite NP as n minus 2p plus 2p. This is clear.
Yeah,
This
that's
is the
very clear.
transformation.
And now, so we want to prove. Obviously, we don't want to prove the claim I mean, for n equals p. It's not supposed to be true. So to prove the claim for n equals p, I want to prove the claim for n equals p plus 1, and then I can procedure by induction up until the point, up until n equals p plus 2. Sorry, up until n equals 2p, right? So how do I prove the claim for n equals p plus 1? We know the claim for n equals, sorry, for n minus 2, because n minus 2 is p minus 1, right? So we know the claim, i.e., we know that gn minus 2 divided by x evaluated at O is 1 over n minus 2 squared. And we also know that hn minus 2 divided by y evaluated at O is 1 over n minus 2 cubed. And we also know the claim for n equals 2, right?
Yes.
Okay, so now I have all the ingredients I need, right? All right. You see this, I want to prove the claim for n equals p plus 1, but I cannot rely on the claim for n equals p. I mean, for n minus 1, because the claim is not supposed to be true for n equals p.
Yes.
So instead, I do a different decomposition. And for n minus 2, I do know the claim. And for 2, I also know the claim. So here I would get, this is right, this is gn hn. But here I will have I will be able to express gn hn as some kind of I mean, elliptic curve sum, or sum of rational functions, where I get this gn minus 2 hn minus 2, and here I have a g2 and h2. Right, and I will do the same, very similar manipulation. I will write the sum on the right side as expressions of gn minus 2 divided by x and hn minus 2 divided by y. And then I would want to evaluate it at O. Right? I mean,
yes.
Okay, you see the point.
Uh-huh.
Okay, I'm not writing the details, but I'm trying to convince you that it's in the same. I mean, it's the same way that we did the previous thing. We can do this. Okay.
And we do it to ensure that n and p are prime. Co-prime.
We do it to be able to keep the induction going. I mean, what is this induction? You have like you have a sequence of propositions, a row, let's say, indexed by the natural numbers. And you want to prove that all the propositions are true. So you prove that row 1 is true. And then you prove that for any n, if rho n minus 1 is true, then rho n is true. This like generalities on induction.
Yeah.
And if you prove these two claims, then you know that all rho n is true. That rho n is rho, if you want, rho k is true for any k. Right? So you kind of, I mean, the induction procedure is like climbing a ladder of proving that each step of the ladder is true. I mean,
so our problem was that when we went one by one for every n, some of them might be not prime to P.
yeah, and we know exactly what are the n's that are not prime to P. You have it's all multiplications of P. It's like
Yeah.
a P times K for various Ks. So we go from 1 up to P minus 1. Here we do the induction ladder. We have no problem. But then we cannot proceed by like trivial induction to n equals P, right?
Yes.
So, but we prove that if the claim is true for P minus 1, then it's true for P plus 1. And then we climb the ladder up to 2P. 2P minus 1.
Okay, I understood.
By the same procedure. I mean, we had in the inductive step is okay as long as we know that n is prime to P, but we cannot move up the induction kind of naively if n is equal to if n is equal to some multiple of P.
So we changed the size of the step in a way that we are sure that they are always prime.
Yeah. So what we did here is like we proved that all the propositions rho 1 up to rho P minus 1 are true. And then we proved that if rho P minus 1 is true, then rho P plus 1 is true. And then the same argument that we had before proves that if rho P plus 1 is true, then rho 2P minus 1 is true. And here we will need to do another jump. We will need to prove, I mean, but it's basically the same. It's the same. That if rho 2P minus 1 is true, then rho 2P plus 1 is also true. This is the same inductive. I mean, it's basically the same trick as here.
Yeah.
Okay, so this is it's kind of a sketch. It's not a foolproof, but I think it's a rather solid sketch. It's like
And it will be the end at 2P plus 1. Or we
sorry?
should go further.
Yeah, we want to prove it for all n prime to P. So we need to be able to do the jump infinitely many times. Every time that we get to a multiple of P, we need to do a jump.
I see.
Okay.
Okay.
So this is kind of there are various versions of induction to collections of statements that are not not so easy to prove in the standard induction. Like, for example, just to maybe trigger your curiosity, I could prove, if I want to prove all the claims rho n, I could prove that for any, okay, I need a base, so I could prove that rho 1 is true. And that rho of 2 to the k is true for any k. And that if rho of, I don't know, t is true, then rho of t minus 1 is true. This is also this three. I mean, if I prove these three issues, then I can conclude that rho of n is true for all n. This is called ascending descending induction. You see why this procedure would work? I mean, because now you give me an n, and you want I want to show you that rho n is true. So what do? I pick so fix n. So to show that rho n is true, choose k such that 2k is bigger than n. There must be some k like this. We know that rho 2k is true. And then rho 2k minus 1 is also true. Because if I have that if rho of t is true, then rho of t minus 1 is true. And I mean, I go down, I have to reach at some point into rho n. And I conclude that rho n is true. You see this like just maybe revealing something about induction that you didn't notice. Yeah, it's clear. Nicholas, you're fine with it? Okay. So what's next? Yeah. Okay. So the next thing we want to do is to calculate the divisor of gm minus gn. This we will not. This will take a few sessions, but one of the tools we are going to need a good notion of derivation of rational functions on E. And remember, we are in an algebraic setting. I mean, there is no way. I mean, we work perhaps over finite fields or over typically over fields of positive characteristic. So there is no apparent geometry, but nevertheless, because we work with polynomials we can differentiate formally. I mean, you know that like the derivative of x to the n, the x is like I mean n x to the n minus 1 dx, right? So we can derive formally this. Sorry, the notation here is it's a bit misleading. This usually you in analysis you write it like this: d of x to the n, and in elliptic curves we have a relation, right? We have I mean, in E, y squared minus x cubed minus ax minus b is equal to 0. So the derivative, whatever I do, the derivative of this thing needs to be 0, right? So, but if I take the derivative, as I know, I do, let me do, instead of small d, I do big D. So if I mean, the derivative of this whole thing, y squared minus x cubed minus ax minus b, needs to be 0. And what I get is 2y times dy must be equal to 3x squared plus a dx. And how do we make it true? I mean, one canonical way to make it true, definition, define a derivation on KE by setting the derivative of x is 2y, and the derivative of y is 3x squared plus a. So you see, if I do it here, the derivative of y is 3x squared plus a, and the derivative of x is 2y, then I get an equality, right? I get here 3x squared plus a is indeed equal to this 2y. Okay, so this is a natural choice of a derivative, and we now want to define the derivative for all rational functions. Rational functions on E, they have two variables, right? X and Y, and they are some quotients of polynomials. But we want the usual properties of derivative. And extending, so I extend D so that it satisfies the usual properties of derivative are one, that the derivative of a constant is 0 for any constant in the field. When I write constant here, I mean the constant rational function, right? The second is that the derivative of the sum of two functions is simply the derivative of the first plus the derivative of the second for any two rational functions. And third, I want the derivative of constant time a rational function is simply constant times the derivative of this function. So for any C in K, and for any R in K of E. And the last rule, this is the most important one. How do I do derivative of a product? R times S. This needs to be R times D of S plus S times D of R. Okay, for any R and S in rational functions only. Now, when I say extend D, I need to kind of show you that there is a unique. Once I set up this kind of anchor condition, and I want these four properties, then there is only one function we want to show, that there is a unique function D from K of E to K of E satisfying let's call these conditions I don't know, I and 2I. So it needs to satisfy I and 2I plus 1 up to 4. But this is not hard. So observe, if I have so I want to do D of x to the n. what is d of x to the n? Let's do d of x squared. D of x squared is x times dx plus x times dx, which is 2 dx. Sorry, 2x dx. Yes.
When you tell that we want to show that there is a unique function that satisfies this property, do we want to say that there is only one function that will satisfy all these properties?
Yeah, that's what unique means.
Okay.
Yeah, unique. This is why, I mean, I want to, I mean, I could have kind of just give you a definition and forget about all the stuff and then prove these properties. But I want to motivate you. So this is kind of one approach to motivate definitions, is that I give axioms that I want the new notion to satisfy. These axioms, they need to be kind of natural, analogous to notions that we already know these properties for. And then I show that there is only one function, one notion that satisfy these axioms. This is usually considered a good motivation for a definition, because then then I know that whatever I wanted, there is only one such thing. I mean,
Okay, I just asked because it didn't sound intuitively for me that there will be only one such function.
yeah, but it is true, and this shows you that this notion of derivation that we are using is canonical. I mean, once you kind of spell out natural properties, there is only one thing that does the trick. Okay, so I'm saying, like, obviously I can. I mean, I start with something d. I know how to derive x. I mean, by 1 and 2. So I simply start with something that, I mean, I know how to do d of x and d of y. And now I want to show you that if the four properties, 1 up to 4, need to be satisfied, then there is only one way to extend d to an actual function from rational functions to rational functions. And the reason is, okay, d of x squared is 2x dx. Then you do d of x cubed. What is it? You can write it by again, this fourth property is the most important. You can write it as x times d of x squared plus x squared times dx. But d of x squared we calculated. This is 2x dx. So this is x times 2x dx plus x squared dx. And I get 2x squared dx plus x squared dx, which is a 3x squared dx. Okay, so this is, and more generally, I mean, you prove by very simple induction that d of xn is n x to the n minus 1 dx. Okay, this is this clear? This, I mean, this just uses the property 4. Now, Lisa, Nicholas.
Yep.
Okay, and now I want to do d of x to the n, y to the k. How do I do it? This is like x by rule number 4. This needs to be x to the n times d of y to the k plus y to the k times d of x to the n. But I mean, I didn't say it, but of course, d of y to the k, by the same procedure, the same reasoning, is going to be k times x to the k minus 1 dy, right? So now I know how to do, I mean, you see, there is only one way to do d of x to the n, y to the k, right? And if I know that, then I know how to do d of any polynomial by rule number, what is it? 2, rule number 2. By rule number 2, I mean, now that I know, I mean, this equation star tells me how to do a d of a monomial. And from rule number 2, I can do a d of sum of rational functions is the sum of the d's. So I get that there is only one way to do d of a polynomial. And then I also know how to do d of r over s is going to be d of r times 1 over s. So there would only be one way to do d of a general rational function. And of course, okay, I didn't say here to do d of a polynomial, I need to use rule number 2 and rule number 3 as well. Actually, I need to use rule number 1, rule number 2, and rule number 3. Because to do a d of a polynomial is like a sum x to the I, y to the j times Cij. And of course, if I and j are equal to 0, then I have the free coefficient. I need to know how to derive the free coefficient, but this, by axiom 1, this is a derivation if it is 0. And I need to know how to derive this monomial, Cij x to the I, y to the j. But I know how to derive x to the n, y to the k. And rule number 3 tells me how to derive constant times a function. Okay, so all these axioms tell me that there is a canonical way to derive a polynomial. And now I want to derive a quotient of polynomials. That's also not a big deal, because a quotient of r over s is just the product of r with 1 over s. And now, if you want to do so, I didn't. Yeah, I guess to do the quotient, you can do the following. So you can show, you just take you take you want to do the derivation of x over y. But this you can do as you know in high school of the derivation of a quotient. It's going to be y dx minus x dy divided by y squared. This would follow from the axioms. I guess you could say, because here n and k can be any integers. They don't need to be positive necessarily. You see, this is I mean, when you derive, for example, you do d of 1 over x, we know how to do it. This is 1 over, this is, sorry, minus 1 times 1 over x squared. So it also fits, the x, of course. So it also fits this this formula star. Okay, so we actually, once we know how to derive x to the power of any integer, then we get the derivative of a general rational function. This is going to be derivative of r times derivative of 1 over s. 1 over s has various, it's like a sum of monomials. So all in all, what I did here, I proved that there is only one function d that satisfies these properties. I will come back to it next time, so of course we will repeat. But any questions for now? Is it clear, or you have problem to even ask?
I have a question, but more like high level. Is where do we sit in the whole scheme of things? Like, where do we sit compared to pairings? Like I'm a bit lost in where are we going and the reasoning of this theorem and the derivation and all this stuff.
Yeah, I said it a bit in the beginning. Maybe you were not here. What we want to prove is this result. We want to know that the n torsion points, when n is prime to p, have a structure of. I mean, we want to understand this group.
Yep.
And pairings, because the Weyl pairing, and in fact all pairings, involve n torsion points.
Yep.
Okay, so whatever we do about pairings will heavily rely on this theorem. So this is in the next 3 or 4 sessions. we will prove this this result. Once we have it, we are essentially ready for defining and proving the properties of the well pairing.
And so the derivation rules that we are starting is still
Okay,
in the
so
same.
so now the derivation thing, we want in the way to, so how do we prove this? What will happen is eventually we will simply be able to say that En has n square points. Once you know that En has n square points, then you have this structure theorem of abelian groups that you can prove with it that En has to be Zn times Zn. But how do you prove that En has exactly n square points? You need to examine the functions Gn and Hn. Okay? And we proved some properties of Hn and Gn. This property should kind of raise a flag that we will eventually use it to count the points on of En. But the current thing we want to do is to calculate the divisor of Gm minus Gn. And I mean, of course, you cannot see it at the moment, but in order to do it, we will need to use derivation.
All right.
So I mean, of course, it's hard to answer to give the full picture. This happens a lot in mathematics. To give like a full answer, I need to give you like the full details, and that's like it
Okay.
opens up over time.
Thanks.
Okay. So have a good weekend, and see you next week.
Thank you very much. Have a nice weekend.
Bye bye.